These are the answers to the ionic bonding practice quiz. In the video description area, there is a link to the practice quiz that accompanies this video. Let's begin with our first question, and the instructions say, each of the following rows of the table below contains an incorrect chemical formula for a binary ionic compound. In the table below, correct the mistake by writing the correct chemical formula. So our first example of a binary ionic compound is lithium nitride. Now on this next slide, you can see that I have listed the common charges that we see for both the positive ions, known as cations, and the negative ions. Those are known as anions. So I've got group 1 plus 1, group 2 plus 2, and then I have group 13 plus 3. And then in groups 15 through 17, I have charges of -3, -2, and -1. So we can see that lithium, Li, is in group 1, and it has a charge of +1. And then we see that the nitrogen ion, which is known as nitride, has a charge of -3. So in order to get the charges on the ions to balance, to produce a chemical formula for a binary ionic compound that would have a total charge of 0, I need 3 lithium ions for every 1 nitride ion. And so that makes the correct chemical formula for lithium nitride Li3N. So I'm going to write that correct chemical formula for lithium nitride in the column on the far right. That is the correct chemical formula. Now, the next example of a binary ionic compound involves the elements magnesium and oxygen. And so the name of that particular ionic compound is magnesium oxide. Let's go ahead and take a look again at the periodic table. And we can see that magnesium, which is located in group 2, would normally have a charge of +2. And then the oxygen, which has the -2, that would be the oxide ion, it has a charge of -2. So we don't need to do anything else to write the correct chemical formula for magnesium oxide. We can simply write the correct chemical formula as MgO because we need 1 magnesium ion for every 1 oxide ion. So that's a slight change, and that the correct chemical formula for magnesium oxide is not Mg2O2, but rather the simplest, lowest whole number ratio that's known as the empirical formula, and that would be listed as MgO, which is the correct chemical formula for magnesium oxide. Now let's move on to our next question, and the instructions for this question say, each of the following rows of the table below contains an incorrect chemical name for a binary ionic compound. In the table below, correct the mistake by writing the correct chemical name. So I'll begin with the ionic compound CaCl2. So that would be Ca for calcium and then Cl for chlorine. And then something else I would like to mention before I look at the details of calcium and chlorine is that many of the transition metals located in groups 3 through 12 and some of the heavier metals in group 14, such as tin and lead, these metals are able to form monoatomic cations that have more than one possible charge. So I'm going to highlight the location of these elements on this slide. Now, the charge of a monoatomic ion is also known as the oxidation state or the oxidation number. And so, for example, I'm going to use iron, which is Fe. The charge or the oxidation state of iron can be either +2 or +3. And so what we do when there is more than one possible oxidation state for a monoatomic cation is that we use a Roman numeral in the name of the ion to indicate the charge of the ion. So I just wanted to mention that information so we can decide, is it appropriate to use a Roman numeral for a particular ion? And then what exactly is that correct Roman numeral? It's going to be the charge on that positive ion or that cation. So again, calcium chloride has a Roman numeral in the name, but that says that that's incorrect. And hopefully you can see that calcium, which is located in group 2, is not in that region that I already mentioned. So it does not need a Roman numeral because calcium is always positive 2. There's not more than one possible charge for calcium. And so therefore I don't need to add the Roman numeral 2 because calcium is always plus 2. So there's my calcium with its charge of plus 2. There's my chloride ion, and I need 2 of them in order to balance the overall charge in this ionic compound. But the correct chemical name for this substance is not calcium Roman numeral 2 chloride, but just simply calcium chloride. So I'm going to write the correct chemical name, calcium chloride, in that column. Now, our next example, it's chromium, and it says that the chemical formula is CrO, and the incorrect chemical name has chromium Roman numeral 1 oxide. So first, let's go find chromium on the periodic table and see if we need a Roman numeral, and then we'll double check and see what the correct charge for that substance is. All right, so CrO. Well, as we can see, chromium, which is listed in the transition metal region in that middle part of the periodic table, it should require a Roman numeral in its name, but we know that Roman numeral 1 is incorrect. So I'll start with the oxide ion, and you can see that oxygen would normally have a charge of -2 as a monoatomic ion. So the chromium is matched with the oxygen. There's a 1-to-1 ratio between the chromium and the oxygen in this chemical formula. And so if oxygen is -2, that means that the charge on the chromium ion must be +2. And so now the correct chemical name for this chromium oxide compound would be based on that Roman numeral for the charge. So it's not Roman numeral 1, it's actually Roman numeral 2. Why is it Roman numeral 2? Because that indicates the charge on the chromium ion in this particular ionic compound. So I'm going to write chromium Roman numeral 2 oxide as the correct chemical name. All right, well, now that we are done with questions 1 and 2 on this practice quiz, let's go ahead and take a look at question 3. And this is a longer question because we have several things to do to fill in the missing information in this table. So the instructions in question 3 say each of the substances listed in the table below represents a binary ionic compound. Fill in the missing information in the table below. So the first ionic compound that is listed in this table has already been filled in for us as an example. The name of the ionic compound is sodium oxide. The symbol and charge of the cation is Na+. The symbol and charge of the anion is O-2, and the chemical formula of the ionic compound is Na2O. So let's go ahead and begin with our next example, which is potassium sulfide. So what I'm going to do is look for potassium and sulfur on the periodic table, and then we can indicate the charges on both the cation and the anion. So there is potassium in group 1. So its charge is +1. And then there is sulfur, which forms the ion known as the sulfide ion, and its charge is -2. So I'll fill that information in the table. So we have K+, and then we have S2-. And with respect to the chemical formula of this ionic compound, let's see if those charges are going to be properly balanced. So clearly, a +1 and a -2 will not be properly balanced. So I'm going to add another potassium ion to make sure that the charges on the positive and negative ions are balanced and that the total overall charge is 0 for this ionic compound. So what is the correct chemical formula of potassium sulfide? Well, it's going to be 2 potassiums and 1 sulfur. So that would be written as K2S. So I will fill in that correct chemical formula into our table. Now let's move on to our next example of an ionic compound. This is strontium bromide. Again, let's go find the elements strontium and bromine on the periodic table so we can figure out the charge on the cation and the charge on the anion. So strontium is located in group 2, so its charge is +2. And bromine is located in group 17, and its charge is -1. So we have Sr2+ and Br-. And now let's go ahead and see if the charges on the ions balance. So what we're going to need to do is add one more bromide ion. So now the charges are balanced. There's an overall charge of 0, but then the correct chemical formula for strontium bromide involves 1 strontium and 2 bromide ions. And so that formula is written as SrBr2. So I'll write that correct chemical formula into our table. And now moving on to our next example, it involves aluminum and selenium. And so the correct chemical name is aluminum selenide. So let's go find aluminum and selenium. So there is aluminum in group 13. It has a charge of +3. And there's selenium in group 16. It has a charge of -2. So we have Al3+ and Se2-. And now in order to get the correct chemical formula, when we have a charge of +3 and a charge of -2, is that it's going to require a little extra thought into how many of these ions do I need to get the overall charge of this ionic compound to be 0. Well, if I add another selenium, that still doesn't balance the overall charges on the ions. And if I add another aluminum, again, the charges are not quite yet balanced, but now if I add one more selenium, everything looks good. So we can see that we have a total charge of +6, and I have 2 aluminum ions, and we have a total charge of -6, and I have 3 selenium ions. So what's my correct chemical formula for aluminum selenide? It's going to be 2 aluminums and 3 seleniums, so Al2Se3, that is the correct chemical formula for the binary ionic compound aluminum selenide. So I will write that correct chemical formula into our table. And then I'll move on to our next example, which is gallium nitride. Again, let's go find gallium and nitrogen on the periodic table. So there is gallium. It's directly below aluminum on the periodic table. It's in group 13, and its charge is normally +3. And then the nitrogen ion, which becomes nitride, is located in group 15, and that would be a charge of -3. Well, now you can realize that unlike the examples with sodium oxide, potassium sulfide, strontium bromide, and aluminum selenide, in which we had to combine them in a proper ratio to make sure that the charges are balanced, these charges are already balanced. So like we saw earlier in this video with magnesium oxide, which was written as MgO because the charge is balanced, all we have to do to write the correct chemical formula for gallium nitride is simply put those two ions together. No numbers, no extra subscripts, just simply GAN, because +3 and -3, they already balance each other out. So that is the correct chemical formula for gallium nitride, which is GAN. And now let's go ahead and move on to our next example of an ionic compound. This is calcium phosphide. So let's go look for calcium and phosphorus on the periodic table to determine the charges. So there is calcium located in group 2. It has a charge of +2. And then there is phosphorus directly underneath nitrogen, that's in group 15, and its charge is -3. So calcium 2+, phosphorus 3-. So we are going to need to do some manipulation to get the charges to balance. Now, if I add another calcium, the charges are still not balanced on these ions. If I add another phosphide ion, again, the charges are not balanced, but then if I add one more calcium ion, now it is looking good. So we have a total charge of +6, and I have 3 calcium ions. and we have a total charge of -6, and I have 2 phosphide ions. So what's my correct chemical formula for calcium phosphide? Well, I've got 3 calciums and 2 phosphorus. That would be Ca3P2. So that is my correct chemical formula for the binary ionic compound calcium phosphide. So I will fill in that formula in our table. All right, only 3 more examples here in question 3. Our next example of an ionic compound is sodium arsenide, and that involves the elements sodium and arsenic. So let's go find those elements on the periodic table to determine the charge on the cation and the charge on the anion. So there is sodium in group 1, and its charge is +1. And then directly underneath phosphorus on the periodic table in group 15 is the element arsenic. And again, the arsenide ion would have the same charge as the nitride ion and the phosphide ion, which is -3. So Na plus and then As3 minus. And so as we put these two charges together, we realize that we need another sodium. Well, that's not enough. We need another sodium. Okay, so now things are looking good with 3 sodium ions for a total charge of +3. And then just that 1 arsenide ion with a charge of -3. So what's our correct chemical formula for the binary ionic compound sodium arsenide? I have 3 sodiums and 1 arsenic, so Na3As is what I write for the correct chemical formula. So I will fill that into our table. All right, 2 more to go. This is rubidium oxide. Let's go find rubidium and oxygen on the periodic table. So rubidium is located in group 1 along with lithium and sodium and potassium. Those would be +1 ions. And then we've seen oxygen before. The oxide ion is -2. So Rb plus, O2 minus. And so as I put these ions together, I need 2 rubidium ions to balance the charge on 1 oxide ion. So the correct chemical formula for the binary ionic compound rubidium oxide would be Rb2O. So I will fill in that correct chemical formula into our table. And then the last one in the table for question 3 in this ionic bonding practice quiz is gallium fluoride. So we've seen gallium already. Gallium is 3+, so +3 for that particular gallium ion located in group 13. And then in terms of the fluoride, it's located in group 17. So fluoride, chloride, bromide, and iodide, those would all have charges of -1. So gallium 3+, fluoride, so F-, and when I put them together, I need not 1 fluoride, not 2 fluorides, but rather 3 fluorides. So now the charges are balanced. I have 1 gallium, which is +3, and I have 3 fluoride ions, which have a total charge of -3. And so what's my chemical formula for the binary ionic compound, gallium fluoride? It would be GaF3. So I will fill in that correct chemical formula into our table. Well, now that we're done with question 3, let's go ahead and move on to question 4 in this ionic bonding practice quiz. So this is question 4. It also has a table that we need to fill in, but you can see that in the previous example, we were going from the correct chemical name to the correct chemical formula. I'm just reversing that process. So here in question 4, I'm giving you the correct chemical formula of the binary ionic compound, and we just have to come up with the name. So the instructions are, each of the substances listed in the table below represents a binary ionic compound. Fill in the missing information in the table below. Now, the next thing I'd like to call your attention to is the name of the cation. It says this may require a Roman numeral. So I'd like to remind you of the information that I had mentioned earlier. So many of the transition metals located in groups 3 through 12 and some of the heavier metals in group 14, such as tin and lead, are able to form monoatomic cations that have more than one possible charge. The charge of a monoatomic ion is also known as the oxidation state or the oxidation number. For example, the oxidation state of iron, Fe, can be either +2 or +3. And if there is more than one possible oxidation state or charge for a monoatomic cation, we use a Roman numeral in the name of the ion to indicate the charge of the ion. So that may show up in this particular question with respect to adding a Roman numeral when necessary. I'd also like to mention that even though on the periodic table we can see nitrogen, phosphorus, and arsenic, you can see from these examples of these monoatomic anions or negative ions that all of their names end with the letters IDE. So nitrogen becomes nitride, phosphorus becomes phosphide, arsenic becomes arsenide. Similarly, we can see that oxygen becomes oxide, sulfur becomes sulfide, selenium becomes selenide. And then for the elements in group 17, fluorine, chlorine, bromine, and iodine, they would be written as ions as fluoride, chloride, bromide, iodide, and so forth. All right, well, now let's go ahead and take a look at our first example, and that involves Li2S is the chemical formula. Let's go find lithium and sulfur on the periodic table. So Li2S, well, there's lithium, but it's not in the transition metal region. It's in group 1, and since lithium is always +1, we don't need to add a Roman numeral in the name of lithium. Now, of course, sulfur becomes sulfide. So there's my lithium, there's my sulfur. Again, the chemical formula has already been given to us as Li2S. I'm just showing you how the charges are going to work out. If you have 2 lithium ions and 1 sulfur ion, you get a total charge of 0. But without a Roman numeral, it's going to be lithium, and again, sulfur becomes sulfide. So there's our correct chemical name for Li2S, just lithium sulfide and no Roman numeral. Now, we will see a Roman numeral a little bit later in this table, but barium is not going to require a Roman numeral, and aluminum is also not going to require a Roman numeral. So let's go ahead and move on to BaCl2. As you can see, barium is not in the transition metal region, so barium is always +2, so it doesn't require a Roman numeral. And as I mentioned, chlorine becomes chloride. So there's our barium +2. Again, this chemical formula has already been given to us. I'm just showing you that we need 2 chlorides for every 1 barium to get a total charge of 0. So just barium, no Roman numeral, and then chlorine becomes chloride. So barium chloride is the correct chemical name for BaCl2. And again, as I mentioned, aluminum also does not require a Roman numeral. So here is Al combined with the fluorine. And again, aluminum is always +3, so no Roman numeral. Fluorine is going to be fluoride, and we need 3 fluorides to balance the charge on 1 aluminum ion. So AlF3 has already been given to us, but the correct chemical name would be aluminum, no Roman numeral, and then fluoride, aluminum fluoride. Now, for these last 3 examples in the table, we have titanium, which is going to require a Roman numeral. We have copper, which is going to require a Roman numeral, and then we have lead, which will also require a Roman numeral. Let's move on to titanium and nitrogen. Now that chemical formula that's been given to us is TiN in a 1-to-1 ratio between titanium and nitrogen. So starting with the nitrogen, which is located in group 15, the nitride ion is going to be -3. If there's only 1 titanium, then the charge on the titanium ion must balance the charge on the nitride ion. So now that I know that I have a charge of +3, that is the Roman numeral that I will use. So it's going to be titanium, which is going to require a Roman numeral. It's one of the transition metals, and it's going to be Roman numeral 3. And again, nitrogen becomes nitride. So titanium, Roman numeral 3, nitride is what I'm going to write in our table. And now copper and lead will also require a Roman numeral. Let's take a look at Cu2O. So again, there's the copper. It's in that transition metal region of the periodic table, so I have to add a Roman numeral because copper, just like titanium, can form more than one possible charge. So I'll start with the oxide ion, which we know is -2. Now, if I had one copper, it would have been +2, but that's not what I see in this chemical formula. I see 2 copper ions. So there's one copper ion, there's another copper ion. Now, to make this work out, to get the 2 copper ions to be balancing the charge on the one oxide ion, hopefully you can see in my diagram that the charge on the copper ion must be +1. And so that is the Roman numeral that I'm going to use. Copper, Roman numeral 1, because the charge on copper is +1. And of course, oxygen becomes oxide. So my correct chemical name is copper, Roman numeral 1, oxide. So I will fill that in our table. And our last example in this table for question 4 is lead combining with sulfur. Now, as I had mentioned in my instructions, not only are these elements in groups 3 through 12, the so-called transition metals, often going to require a Roman numeral, but I had mentioned some of the heavier elements in group 14, such as tin, Sn, and lead, Pb. They also can form more than one possible positive charge. Sometimes they're +2, sometimes they're +4, and as we can see in this example, the lead is combined with not one sulfur, but 2 sulfurs. So if you know that the charge on the sulfide ion is -2, but you have 2 of them in this ionic formula, the charge on the lead is going to be +4. And hopefully you can see how that works out. The total charge of the 2 sulfur ions is -4. Therefore, the charge on that single lead ion would have to be +4 to give you an overall charge of 0 and balance the charges. So what's my name? It's going to be lead, Roman numeral 4, and again, sulfur becomes sulfide. So lead, Roman numeral 4, sulfide is the correct chemical name, and I will fill that in our table. And so now that is the end of question 4. Let's go ahead and move on to question 5. Now, question 5, which is the last question in this ionic bonding practice quiz, is a little bit different than the other chemical formulas of the ionic compounds that we've seen so far in this video. And that's because each of the substances listed in the table below represents an ionic compound that contains a polyatomic ion. So we still have to fill in the missing information in the table below, but some of you watching this video might say, what exactly is a polyatomic ion? So when I taught this particular information to my students in my chemistry class, I only picked 8 polyatomic ions that I asked them to memorize. Now, in the world of chemistry, there are so many more examples of polyatomic ions, so I just narrowed down the list to these 8. So we can see that ammonium is listed with a chemical formula NH4 + 1. So why is that a polyatomic ion? Because it contains more than one atom. It contains 1 atom of nitrogen and 4 atoms of hydrogen. And the overall charge on that polyatomic ion happens to be +1. And then you can see in the table at the top of this slide, we have hydroxide, which is OH, has an overall charge of -1. It contains an oxygen and a hydrogen atom. So again, a polyatomic ion, more than one atom, combined together to produce a group of atoms that has an overall charge. And the overall charges that I'm showing you in this table are either +1, -1, -2, or minus 3. And so what I told my students in my chemistry class is that the names and formulas of these 8 polyatomic ions should be memorized. Now, they can make flashcards, and flashcards are a fine way to review and practice when you're trying to memorize something. But as you can see on this slide, I wrote a little song to help them memorize these 8 polyatomic ions. And again, there's way more than 8 polyatomic ions that are existing in the world of chemistry. I just narrowed it down to these 8. So what I'll do is just kind of show you how that song works. And so the way the song works, I've grouped the ions that have the same charge together. So the first part of the song involves the ions that have a charge of -1, and that includes hydroxide, chlorate, and nitrate. And then the next part of the song groups together the polyatomic ions that have a charge of -2, and they are carbonate, chromate, and sulfate. And so then there's only 2 more ions in our list. There's one of them which is NH4, and that's +1, and that's different than all of the others because all of the others are negative. This one is the only cation, it's positive. And again, there's phosphate, which happens to be -3. So what I'll do is I will go ahead and sing you that polyatomic ions song. It's sung to the tune of Jingle Bells, but you are welcome to make flashcards. And if you'd like to sing, I'm sure you have a better voice than I do. All right, here it goes. So the beginning part is all the -1 ions. OH is hydroxide, ClO3 chlorate. Their charges are both -1 like NO3 nitrate. Carbonate is CO3, chromate CrO4. Their charges are both -2 like sulfate SO4. NH4, NH4, NH4 +1. It's the only cation, it's called ammonium. Phosphate is PO4, its charge is -3. Polyatomic ions are so fun for you and me. Now again, if you're not a good singer or you don't think that that's going to work, make your flashcards, and that would be a fine way to do it. So as we go ahead and take a look at the table here in question 5, I'm going to begin by finding all 8 of those polyatomic ions. And I'm going to fill in the table with all of the polyatomic ions from that list. So again, you can see that sodium hydroxide has already been filled in for you as an example. That's the first part of the polyatomic ion song that begins, OH is hydroxide. And I can see that hydroxide is actually listed at the bottom of this table. It says strontium hydroxide. So again, that's OH -1. The next part of the song after the OH is hydroxide is ClO3 chlorate. So let's go look for chlorate, and we can put ClO3 -1 into our table. So there it is. That's called chlorate, ClO3 -1. And then the next part of the song goes, their charges are both -1 like NO3 nitrate. So let's go look for nitrate as NO3 -1. There's nitrate, NO3-. So now we found all of the -1 polyatomic ions, which is the first part of the song. Now let's look at the next part of the song, which is carbonate is CO3. So I'm looking for a CO3 -2 for carbonate. So there's carbonate, CO3, 2-. The next part of that song goes chromate, CrO4. So I'm looking for chromate, CrO4, 2-. So there's chromate, CrO4, 2-. And then there's one more -2 ion from that song. It says their charges are both -2 like sulfate SO4. So I'm looking for SO4, 2-. So there's sulfate. It's actually written twice in this table. So it's SO4, 2-. And now I have only 2 more left. So there's the Jingle Bells part of the song. NH4, NH4, NH4 plus 1. It's the only cation, it's called ammonium. So I'm looking for ammonium, there it is, NH4 plus 1. And then phosphate is PO4, its charge is -3. Polyatomic ions are so fun for you and me. So there's phosphate, PO4, 3 minus. And so now I'm not done with this table, but I have found all 8 of the polyatomic ions that I have asked my students in my chemistry class to memorize. So what's left? Well, what's left are all the monoatomic ions. So for example, sodium is a monoatomic ion, it's Na+. Let's go find barium on the periodic table. So barium is in group 2. Its charge is +2, so Ba, 2+. And then let's go find potassium on the periodic table. So potassium is located in group 1. Its charge is +1, so K+. And then our next examples in the table are nickel Roman numeral 2 and then copper Roman numeral 2. So when they give you the Roman numeral, they're telling you the charge on that ion. So it's going to be Ni, 2+ for nickel, Roman numeral 2. And then again, copper is also Roman numeral 2, so that's going to be Cu for copper, and then 2+. And then we have magnesium, aluminum, and strontium. All right, well, magnesium is in group 2. That's going to be +2, so Mg, 2+. Aluminum is located in group 13. That would be Al, and its charge is +3, so Al, 3+. And then strontium is located in group 2, so below magnesium and calcium. So it's also +2, so Sr, 2+. Well, now we're almost done with filling in this table. What do we have to do now? Write the correct chemical formula of the ionic compound. And since we already know the symbol and the charge of the cation, and we know the symbol and the charge of the anion, all we have to do is put them together in the proper ratio so that the total charge in this chemical formula is 0. So let's start with the correct chemical formula for ammonium sulfate. So ammonium sulfate contains NH4 plus and SO4 2-. So hopefully you can see from the examples that I've shown you so far in this video that NH4SO4 is not going to work because the charges on the ions are not balanced. But notice what happens if I add another ammonium ion. Now I've got 2 ammonium ions for a total charge of +2, and then that balances the charge on the 1 sulfate ion, which has a charge of -2. But you'll also notice that we have an issue that has not come up before in the other examples in this video, is that what do we do when we have a polyatomic ion and we need more than one of that polyatomic ion? Well, if you need more than one ammonium, this is what you do. You wrap parentheses around the chemical formula of that polyatomic ion. So in this case, I wrapped parentheses around the NH4, and then because I need 2 ammonium ions in this formula, I put that 2 as a subscript outside the parentheses to show that the NH4 is being multiplied by 2. And then SO4, I did not put any parentheses around it because I only need 1 of the sulfate ion. So it's NH4 inside parentheses times 2, there's that subscript 2, and then SO4. All right, our next example is barium chlorate. So if I have barium, which is 2+, and I have chlorate, which is ClO3 -1, again, you can see that those charges are not balanced until I add another chlorate ion. So now I'll do the same thing I did with the ammonium sulfate. There's a polyatomic ion, this is chlorate, and it's ClO3. I'm going to wrap that in parentheses, and then I'm going to put a 2 on the outside of the parentheses to show I need 2 chlorate ions for every one barium ion. So the correct chemical formula of barium chlorate is Ba, and then ClO3 inside parentheses times 2 with that subscript outside the parentheses. All right, our next example is potassium carbonate. Now, I won't need any parentheses in this chemical formula because I have one polyatomic ion, which is the carbonate ion, and that is -2. And I will have to add another potassium ion to balance the charge, but potassium is not a polyatomic ion. So I can just put a 2 after the K symbol. I don't need to wrap parentheses around the K because that's a monoatomic ion. So K2CO3 is the correct chemical formula for potassium carbonate, and it represents the fact that I need 2 potassium ions for every 1 carbonate ion in order to balance the charges on the ions and give me an overall charge of 0. Now, in our next example, we've seen examples like this before with magnesium oxide and gallium nitride. You don't have to do anything with respect to balancing the charges on the ions because they're already balancing each other. So nickel happens to be +2. The chromate ion happens to be -2. And when you put them together, the charges are already balanced. So all I have to do is write NiCrO4. No parentheses, no extra subscripts or numbers added, just a 1-to-1 ratio between nickel +2 and chromate CrO4 -2. In our next example, we have copper, which happens to be +2, and we have nitrate, which happens to be -1, and so I will need another nitrate ion in my formula to balance the overall charges. So I'm going to do the same thing I did with barium chlorate. I'm going to write the first element just as the element, so Cu, but then I wrapped parentheses around the nitrate ion, and then I put a 2 on the outside of the parentheses to show I need 2 nitrate ions for every 1 copper 2+ ion. So the correct chemical formula for copper Roman numeral 2 nitrate is Cu, and then parentheses around the NO3 with that 2 on the outside of the parentheses to show I have 2 nitrate ions. All right, our next example is magnesium phosphate. Now, 1 magnesium and 1 phosphate are not going to balance each other out because magnesium is +2 and phosphate is -3. If I add another magnesium, the charges are still not balanced. If I add another phosphate ion, I'm getting closer, but the charges are still not balanced, and so hopefully you can see that we need 3 magnesium ions for a total charge of +6. We need 2 phosphate ions for a total charge of -6. I will need parentheses in my chemical formula around the PO4. So it's going to be written as Mg3 because I have 3 magnesium ions, and then the PO4, the phosphate, I've wrapped parentheses around the PO4, and I put a 2 on the outside of that parentheses to show I have 2 phosphate ions in this chemical formula. So Mg3, parentheses around the PO4, 2. All right, we got 2 more examples, and then we are done with this ionic bonding practice quiz. So I hope that all of these answers and explanations have been helpful so far. So 2 more to go. All right, this is aluminum sulfate. Now the Al ion happens to be +3, but the sulfate, the SO4, happens to be -2. So I need another sulfate, but that's still not enough to balance the charges. I will add another aluminum, almost there, but still not perfectly balanced. And then hopefully you can see why we need 2 aluminum ions for a total charge of +6. We have 3 sulfate ions for a total charge of -6. I am going to need parentheses around the SO4 because I have more than one of that polyatomic ion. So 2 aluminums, Al2, wrapping parentheses around the sulfate SO4, and then that 3 as a subscript outside the parentheses tells me I have 3 sulfate ions in that formula. So Al2, parentheses around the SO4, and then there's the 3 subscript. All right, our last example is strontium hydroxide. So I've got one strontium, which happens to be +2. I've got an hydroxide ion, which is only -1, so the charges don't balance. I need another hydroxide, and now the charges are balanced. I still need parentheses around the OH to show that I have two of them. So it's going to be Sr, and then parentheses around that polyatomic ion hydroxide, and then there's that 2 on the outside of the parentheses showing me I have two hydroxide ions. So Sr, OH in parentheses, and then there's the 2 on the outside. All right, well, this was the last question in this ionic bonding practice quiz. So we have come to the end of this video. Again, I hope that all of these answers and explanations have been helpful. Thanks for watching, and good luck studying for your ionic bonding quiz.